If you met Lisa Piccirillo in 2018, you would not have guessed that she was about to topple one of the most long-standing problems in mathematics. You would not have guessed that she was on the verge of solving a problem that had survived untouched and mocking for half a century. At the time, she was one of many graduate students at the University of Texas at Austin. She had grown up in Greenwood, Maine, a town so small that if you blinked while driving through it, you would miss the post office and the general store. The population was under 900 people. Her father was a welder. Her mother was a middle school math teacher. There was no legend of the child prodigy here. There was no story about her deriving calculus at age 4. She was an overachiever, sure, but in the way that kids in small towns are often overachievers. She rode dressage horses. She played in the band. She acted in drama club. She was active in her church youth group. She was just busy. When she went to college at Boston College in 2009, she was just as interested in theater as she was in numbers. She was a normal person. So when she stumbled across the Conway knot, she did not even know that it's a problem that has been open for half a decade. She saw it as a practice exercise to test some of the mathematical tools she had been developing. She did not know that famous men with tenured chairs at Ivy League universities had spent decades banging their heads against this specific loop of string. She just thought it looked interesting. She thought it might be a nice thing to think about on evenings and weekends, for fun. She treated the 50-year-old mystery like a Sunday crossword puzzle. And because she did not know she was supposed to fail, she did not fail. She solved a 5 decades-old problem within a week. A few days later, Piccirillo knocked on the door of her professor, Cameron Gordon's office. "I think I solved the Conway knot problem," she said. Gordon looked at her. He blinked. "What?" She showed him the proof. Gordon read it. He is one of the few people in the world who could verify it on sight. He traced the logic. It held up. He looked up at her again. He started yelling. "Why aren't you more excited?" he shouted. He was freaking out. He knew exactly what this meant. This wasn't just a homework problem. This was the holy grail of low-dimensional topology. This was the end of a 50-year quest. "That's going to the Annals right now," he said. The Annals of Mathematics is the most prestigious journal in the field. It is published by Princeton University. Getting a paper in the Annals is like winning an Olympic gold medal. It makes your career. Piccirillo was bewildered. "I don't think she'd recognized what an old and famous problem this was," Gordon said later. She had just stumbled into history. Lisa Marie Piccirillo, born around 1990, hails from the quiet, wooded landscape of Greenwood, Maine. The town has a population of fewer than 900 people. There were no math circles or Olympiad training camps in her daily life. Instead, her world was filled with the earthy realities of rural New England. Her upbringing was diverse in its activities. She attended Telstar Regional High School in the nearby town of Bethel. It is a public school that serves the local community, and Piccirillo was an enthusiastic participant in everything it had to offer. She rode dressage, navigating horses through intricate patterns that perhaps foreshadowed her later work with topological loops. She was active in her church youth group. She played in the school band and acted in drama productions. Her mother, Ingrid, was a middle school math teacher, which gave Lisa an early, albeit standard, introduction to the subject. Her father, Paul, worked as a welder and in sales. In her interviews, Lisa recalls that she was not the type of child who was programming computers or building complex algorithms at age 4. She was a normal, active kid who happened to be good at school. Despite her mother's profession, Lisa did not view herself as a mathematician in training. Because she was good at math and science, people told her she should be an engineer. She dutifully attended engineering summer camps, but the experience left her cold. She found herself bored by tasks like building bridges out of popsicle sticks. She was the valedictorian of her class, but in a small town. She did not know that she was preparing for a career that would land her on the pages of international newspapers one day. In 2009, Piccirillo left the woods of Maine for Boston College. She arrived with the vague intention of studying science or math, but without a clear career path. She even considered becoming a journalist if the math route did not work out. Her freshman year was a turning point. She enrolled in a calculus class, a standard gateway course for STEM majors. She did not perform exceptionally well by the standards of a golden child prodigy. She struggled at times. Yet, her professor saw something in her. That professor was J. Elisenda Grigsby, a mathematician who became a pivotal mentor in Piccirillo's life. Grigsby noticed that while Piccirillo might not be the fastest calculator in the room, she possesses a deep creativity and a refusal to accept things at face value. She urged Lisa to take more advanced classes, specifically linear algebra. It was in her first year at Boston College that Piccirillo attended a lecture that changed the trajectory of her life. The talk was about weird, smooshy surfaces embedded in space. The speaker described objects that could be stretched and deformed without changing their fundamental properties. This was Piccirillo's introduction to topology. She was captivated. Topology is often described as rubber sheet geometry. It is a world where a coffee cup and a donut are considered the same object because one can be stretched into the shape of the other without tearing or gluing. During her time at Boston College, Piccirillo maintained her diverse interests. However, she also began to feel the first twinges of what many women in mathematics experience. She worried that she would have to sacrifice her personality to succeed in the field. She completed her Bachelor of Science in Mathematics in 2013. Her undergraduate years were also where she began to confront the reality of being a woman in a male-dominated field. The textbooks were written by men. The famous theorems were named after men. The image of the mathematician was almost exclusively male. Yet, she had Grigsby as a counterexample. Seeing a woman in a position of authority was instrumental. After graduating from Boston College, Piccirillo chose to pursue her PhD at the University of Texas at Austin. UT Austin had a stellar reputation for its topology program and was known as a welcoming place for female mathematicians. Graduate school was a liberation. In Austin, she found a community of mathematicians who were interesting humans and not geniuses in the intimidating sense she had feared. She worked under the supervision of John Edwin Lueck, a respected topologist. Her research focused on 3- and 4-dimensional spaces, the very objects that had fascinated her since that first lecture at Boston College. She dove into the study of knot traces and the slice genus, the topics that eventually formed the basis of her dissertation. Piccirillo was an active and respected member of the department, building a solid career. She took on a mentoring role for younger students and organized the Distinguished Women in Mathematics lecture series. She focused on becoming an expert in her field, mastering key topics like invariants, mathematical labels used to distinguish knots, and 4 manifolds, which are complex spaces that extend our 3-dimensional reality. By the summer of 2018, Lisa Piccirillo was nearing the end of her PhD program. She had developed a set of techniques involving knot traces, a way of building a 4-dimensional space by attaching a handle to a knot in 3 dimensions. She was looking for places to apply these tools. She did not know it yet, but she was perfectly positioned to solve a problem that had stumped the giants of her field for half a century. To understand what Lisa Piccirillo did, one must first understand the playground in which she works. Knot theory is a branch of topology that studies closed loops in space. In the everyday world, a knot is a tangle in a shoelace or an extension cord. In mathematics, a knot is the same tangle, but with the loose ends fused together to form a continuous closed loop. Once the ends are joined, the knot is trapped. It cannot be untied by simply pulling on the strands. Mathematicians want to know when two knots are actually the same. If you twist and pull a tangled loop without cutting it, can you make it look like a perfect circle? If you can, it is an unknot. If you cannot, it is a true knot. This seems simple, but as the number of crossings in the tangle increases, the complexity explodes. The Conway knot is a specific tangle with 11 crossings. It was discovered by John Horton Conway, a legendary and playful British mathematician, in 1970. Conway was a giant in the field, known for his game of life and his contributions to many areas of math. He identified this particular knot and included it in his list of knots with 11 crossings. For decades, it was just one of thousands of knots, but it had a secret. The problem with the Conway knot concerns a property called sliceness. This concept requires stepping out of our three-dimensional world. Imagine a sphere in three-dimensional space, like an orange. If you slice the orange with a two-dimensional knife or a plane, the cut surface is a circle. Now imagine moving up a dimension. Imagine a sphere in four-dimensional space. If you slice this 4D sphere with a three-dimensional knife, our 3D space, you might get a knot. A knot is slice if it can be the boundary of a smooth disk existing in four-dimensional space. Think of the knot as the crust of a slice of bread. The bread itself is the disk. But this bread exists in 4D. If the knot is the boundary of such a smooth, non-self-intersecting disk, it is slice. If it is not slice. This property is fundamental because it connects the study of knots to the study of four-dimensional spaces, which are notoriously strange. In 4D, things can happen that are impossible in 3D. Loops can untie themselves by passing strands over one another in the fourth direction. For 50 years, mathematicians had determined the slice status of every knot with fewer than 13 crossings. There are thousands of them. They had checked them all, except one, the Conway knot. The Conway knot was a stubborn outlier. It was known to be topologically slice, meaning it could be the boundary of a crumpled, rough disk in 4D. But no one knew if it was smoothly slice, meaning the boundary of a smooth, unwrinkled disk. The distinction matters immensely in the world of 4D topology. You might be asking yourself, if we could solve thousands of such knots, why is the Conway knot so hard? The difficulty in analyzing the Conway knot stems from its mutant nature, a unique characteristic that gives it a superpower. This knot is a close relative of another knot called the Kinoshita-Terasaka knot, which is already known to be smoothly slice. The Conway knot is created through a subtle mutation. A section of the Kinoshita-Terasaka knot is excised, flipped, and then reattached. Because this mutation is so minor, the Conway knot retains nearly all the same invariants as its sliceable counterpart, making its distinction particularly challenging to identify. Mathematicians rely on a set of tools called invariants that function like fingerprints or blood types to distinguish between different knots. Examples include the Alexander polynomial, the Jones polynomial, and the potent modern Rasmussen's S invariant. If an invariant indicates a knot is not a slice knot, then it is conclusively proven not to be one. However, the Conway knot proved elusive to these tools because it is a mutant of a slice knot. All calculated invariants for the Conway knot returned results suggesting, but it resists definitive proof. This specific problem had become a legend in the field. It was the one blank spot on the map. Every time a new invariant was discovered, mathematicians would rush to test it on the Conway knot, hoping it would finally reveal the truth. And every time, the knot would pass the test, revealing nothing. In the summer of 2018, Lisa Piccirillo attended a conference on low-dimensional topology and geometry. She sat in a lecture hall, listening to speakers discuss the open problems in the field. One speaker, Shelley Harvey of Rice University, mentioned the Conway knot. She showed a slide of the 11 crossing snarl and explained that it was the last holdout. No one knew if it was slice. Piccirillo listened, but she did not think she was about to make history. She thought it was a nice little problem. It seemed like a good testing ground for the tools she had been building for her PhD thesis. I didn't allow myself to work on it during the day, she said later, because I didn't consider it to be real math. I thought it was like my homework, she has said. If she had known how hard it was supposed to be, she might never have tried. She was taking her tools for a joyride. She didn't know that people had spent careers banging their heads against this wall. Her approach was ingenious in its avoidance of the knot's trap. She knew that calculating invariance directly on the Conway knot was useless. The knot would just mimic its slice sibling. So, she decided to replace the knot. Lisa used a concept called the trace of a knot. The trace is a specific four-dimensional space constructed by attaching a 4D piece to the knot. She knew that if two knots have the same trace, they share the same slice status. If she could find a different knot that had the same trace as the Conway knot, she could study that new knot instead. She spent her evenings twisting and untwisting mental and paper loops. She used Rolfson twists, operations that alter a knot without changing the 4D manifold it generates. By carefully twisting the Conway knot, she produced its trace sibling. This new knot, the Piccirillo knot, was messy. It had more crossings. It looked nothing like the elegant 11-crossing Conway knot, but it had two key virtues. It shared the trace of the Conway knot. It was not a mutant of the Kinoshita-Terasaka knot. Because it wasn't a mutant, it had lost the Conway knot's camouflage. Piccirillo calculated the Rasmussen S invariant for this new knot. For slice knots, the S invariant is 0. She ran the calculation. The S invariant for the Piccirillo knot was not 0. This was the smoking gun. Because the S invariant was non-zero, the Piccirillo knot was not slice. Because the Piccirillo knot and the Conway knot share the same trace, if one is not slice, the other cannot be slice. Therefore, the Conway knot is not slice. It was over. In less than a week, using evenings and spare moments, the graduate student from Maine had solved the 50-year-old riddle. She had proven that the Conway knot is not slice. Lisa did not immediately realize the magnitude of what she had done. She thought she might mention it to a few people. She considered putting it in a minor journal or perhaps not publishing it at all. A few days later, she walked into the office of Cameron Gordon, a senior professor at UT Austin and a renowned topologist. She casually mentioned her result. "I solved the Conway knot problem," she effectively said. Gordon's reaction was explosive. He started yelling. "Why aren't you more excited?" he shouted. He sort of freaked out, Piccirillo later recalled. Gordon realized instantly that this was not a homework assignment. This was a major breakthrough. He told her, "That's going to the Annals right now," referring to the Annals of Mathematics, one of the most prestigious journals in the field. The news spread quickly through the tight-knit topology community. Joshua Green, a professor at Boston College who had supervised Piccirillo's undergraduate thesis, heard the news. He was stunned. "It was really gratifying to see somebody I'd known for so long suddenly pull the sword from the stone," he said. The paper, titled simply "The Conway Knot is Not Slice," was submitted to the Annals of Mathematics on the 15th of August 2018. It is concise. It was accepted in September 2019 and published in early 2020. The speed of acceptance and the prestige of the journal confirmed what Gordon had known immediately. This was a landmark result. For Piccirillo, the attention was a mixed blessing. She is happy to have solved the problem, but she is wary of the genius label that comes with it. She wants to be seen as a working mathematician, not a wizard. For a mathematician who eschews the genius label, the attention was surreal. She was hailed as the graduate student who outsmarted the experts. Quanta magazine ran a feature detailing her joyride discovery. The New York Times, Boston Globe, and Smithsonian Magazine followed. I'm having to relearn how to be okay with the fact that most of the time I'm failing to prove really simple stuff when I'm feeling the weight of these expectations, she told the Boston Globe. In 2021, she was awarded the inaugural Maryam Mirzakhani New Frontiers Prize, an award created to recognize outstanding early career women in mathematics. The prize is named after the late Iranian mathematician who was the first woman to win the Fields Medal. She also received a Clay Research Fellowship and a Sloan Research Fellowship in the same year. You don't have to be really smart, whatever that means, to be a successful mathematician, she said. MIT, the pinnacle of technical education, offered her a tenure-track position. She accepted, becoming an assistant professor in July 2020. However, the pull of Austin remained. After 4 years at MIT, Piccirillo returned to the University of Texas at Austin in 2024, this time as a full professor holding the Sid W. Richardson Foundation Regents Chair in Mathematics. It was a homecoming. She returned to the department where she had been a graduate student, now as one of its most celebrated faculty members. Her work on the Conway knot has opened new doors in topology. The technique she used, utilizing trace siblings to bypass the limitations of invariance, is now part of the standard toolkit. She is back, with Cameron Gordon and the Topology group. Her work will help improve topology applications, such as in computer networking, where the specific arrangement of nodes and links determines how efficiently data flows across the internet and local systems. In biology, topological concepts help researchers understand how long DNA strands knot and coil within cells, as well as how proteins fold into functional 3D shapes. Further, robotics relies on topological maps for motion planning, enabling machines to navigate complex environments without getting stuck. Topological data analysis, called TDA, allows scientists to identify hidden structures and patterns within massive, noisy datasets. John Conway, a man who loved games, puzzles, and the unexpected, would have adored her proof. He died in April 2020, just 2 months after Piccirillo's paper was published. He was 82 years old. We don't know if he fully understood the proof before he died. His health was failing, but word reached him that the problem had been solved.